Well, hello, thanks for joining us today. In this session, we want to solve another problem in heat transfer. Problem number 235. But like always, let me introduce the reference, which is heat transfer from Mr. Holman. Okay, problem number 35 is the problem I want to solve it. Then let's go and get started. Consider a shielding wall for a nuclear reactor. A shielding wall for a nuclear reactor. The wall receives a gamma ray flux such that it is generated within the wall according to the relationship, like this relationship. This is kind of exponential relationship. Q dot equals Q dot node time e to the power minus a x, where Q dot O is the heat generation at the inner face of the wall exposed to the gamma ray flux, and A is a constant. This A is a constant. So using the relation for a generation, derive an expression for the temperature distribution in a wall of thickness L, where the inside and outside temperatures are maintained at Ti and To respectively. Also obtain an expression for the maximum temperature at the wall. Okay, let's get started. Let's go to the whiteboard and get started and solve this problem. Okay. First, like always, I should draw a picture for that. These are gamma rays which go inside the wall with thickness of L and go out from the other side. Okay. Then the heat generation, Q dot is Q dot O E minus A X. Okay. And A is constant, and X is distance from this T. Temperature I is temperature inside temperature, and this is TO outside temperature. Okay. We had a differential equation, second order differential equation for temperature, like this. The 2T AX2 plus Q dot divided by K, which is thermal conductivity. Thermal conductivity equals 0, which is kind of homogeneous differential equation. We should solve this problem, this differential equation to have the formula for temperature. Okay, then let's do it. Okay, undo T divided by D, it's 2 equals minus Q dot O E minus AX. I put these equation in place of this Q dot divided by Q. Okay, and this negative is because this term will go to the right of the equation. Then okay, then the T or the x equals minus q dot o k integrate of e minus ax dx, okay, which will be positive of, if you solve this integral, you will earn this one, ka e minus ax plus c1, which is a kind of constant for this integral, okay. Then t equals, if I integral from this equation, I would have T temperature profile. It will be q dot o ka2 e minus ax plus c1 x plus c2, okay. But I have to, this is like that. T equals integral of q dot o k a e minus ax plus c1 dx, okay, which is integral of this one, okay. And after that it will be something like this one, okay. Then I have to find these two constants. Okay, if I put the boundary condition here, x equals 0, and for this one x equals L, okay. If I put these two, for example, ti in place of t and 0 in place of x, it will be ti equals minus q o k a e, oh sorry, made a mistake, yeah, plus c2, okay. And for to, if I put to in place of t and l in place of x, it would be to equals minus q dot o over k a square e to the power of minus l, exponential of minus al plus c1l plus c2, okay. And from these two equation, I will able to find c2 is ti plus q dot o over ka, and c1 will be minus q dot o over ka square multiplied by 1 minus exponential of minus al and minus ti minus to, all of these divided by l. This is c1, okay. And then if I put c1 and c2, this formula and this one, to in place of these and these, okay. c1, this relationship here, and this relationship here, I would have the main formula for temperature. It would be something like that, minus q dot o divided by ka square e minus ax minus 1 plus x over l multiplied by 1 minus e to the power of l, okay, minus ti to x over l plus ti. This is the main formula for temperature, okay, the relationship for temperature. So this is the first section first section of the question. First section. Okay, but about the second section of the problem, I have to, let me erase these one because I didn't need them. Okay, then this is the formula, our formula. Okay, this is the first section of the problem. Then I have to find maximum temperature, T max. Okay, for finding the T maximum temperature, I have to find X of temperature, max temperature. Then these relationship have some diagram like that. For example, here is minus Q dot O over Ka2. This relationship, this is this point. Then this is exponential relationship. It has a relationship something like that. Okay, this is temperature. If it would be T and this is X, this is temperature. Okay, we have to find maximum temperature, which is someplace like here. Okay, then for that, this is X max. For that, for this point, for finding this point, we have to derive of this formula to the X like that, dt dx equals, and put it equals 0. Okay, and find X. Then let's derive from this formula. It would be minus QO, okay, minus QO, Ka2 minus AX, okay, plus 1 over L, 1 minus AL, Ti minus To over L equals 0. Okay, if I want to find that, okay, if I want to find that E minus AX equals minus TO L, okay, that's some problem. The marker, okay, Ka2, this is L, this is Ti, sorry for this problem, but by 1 over L, 1 minus E minus L. Okay, if I want to find X, I have to put an ln here. Okay, minus 1 over A ln of kind of logarithm, 1 over L 1 minus E A L. Let me change the marker and write it again. Sorry. With a better color, okay? X equals 1 over A ln of 1 over L 1 minus exponential of 1AL plus K A Q node, okay, T I minus T O, okay. This is our X, okay, X max, better to say X max. Okay, if we want to find temperature of this point, we have to put this X into this formula, okay. If we want to find this temperature, we have to substitute this maximum X. This is this tense, this formula is for that, and put it inside the X, okay. Then this temperature, maximum temperature, which is this is temperature maximum, then T max equals T when X is maximum, okay. Then this is related to TO, which is temperature of outside wall, and TI, temperature of inside wall, and thermal conductivity of the material, Q dot O, and constant, which is A, and we don't know it, is kind of constant, and L, the thickness of the wall, and just that. If we find X and put it inside the this formula, we are able to find maximum temperature in the wall, okay. It was the solution of these problem. I hope you enjoy this formula, this solving, and enjoy from this session. Take care, have a good one, bye bye.